Hi everyone, in this video we will show how to solve non-exact differential equations. Now recall from the previous video that a differential equation of the form this is exact if the partial derivative of m with respect to y equals the partial derivative of n with respect to x. Now this equation is non-exact if m sub y is not equal to n sub x. Now, a non-exact differential equation can be made exact by multiplying by an integrating factor mu. Now, the process of finding integrating factors can be quite difficult. So in this video, we would only consider two cases. Now, the first case states that if the partial derivative of m with respect to y minus partial n with respect to x over n is a function of x alone, then the integrating factor is exponential of integral of f of x dx. And then the second case states that if partial n with respect to x minus partial m with respect to y over m is a function of y alone, then the integrating factor mu of y equals the exponential of integral of f of y dy. So we'll look at an example to illustrate these cases. Now, example 1, find an integrating factor for 3x squared y dx plus 3x cubed dy equals 0, and then solve. So for this, our m is 3x squared y and n is 2s cubed. Now the partial derivative of m with respect to y equals, so we differentiate this guy with respect to y, treating x as a constant. So we have 3x squared. And then the partial derivative of n with respect to x is 6x squared. Now we see that m sub y is not equal to n sub x. That shows that this equation is not exact. So we need to find an integrating factor to make it exact. So how do we do that? Let's check case 1. For case 1, we need to check that m sub y minus n sub x over n is a factor of x alone. So let's check that. M sub y is 3x squared minus n sub x is 6x squared over n. N is 2s cubed. And this gives minus 3x squared over 2x cubed. And this gives us minus 3, now this is x cubed, 3 over 2x. This cancels this, so we have just one left. So this is a function of x alone. M sub y minus n sub x over n gives a function of x alone. So by the first theorem that we stated, it implies that we have an integrating factor of the form exponential of integral of minus 3 over 2x dx. And this is equal to exponential minus 3 over 2 1 over x dx. And this gives us the exponential of minus 3 over 2 integral of 1 over x ds is ln x. This is equal to exponential ln x minus 3 over 2. This is by the law of logarithm. And this gives x to the power of minus 3 over 2. We now multiply the original equation by this integrating factor. That is, we multiply, we have x to the power of minus 3 over 2 times 3x squared y dx plus x to the power of minus 3 over 2 times 2x cubed dy equals 0. Now, by the law of indices, we can add up the powers of x. Minus 3 over 2 plus 2 gives 1 over 2. So we have 3x to the power of 1 over 2y dx plus we multiply the powers of we multiply x to the power of minus 3 over 2 times x to the power of 3. So by indices, we can add up the powers, and that gives us 2x 3 over 2 dy equals 0. Now we now have a new m and a new n. So if we differentiate the new m partially with respect to y, we get 3x raised to power half. And then if we differentiate the new n partially with respect to x, this gives 3 over 2 times 2 x. 3 over 2 minus 1 gives 1 over 2, and this gives 3x to the power of half. So m sub y equals n sub x, and so it shows that the new equation is exact. Now, since it is exact, it implies that there exists a function f of x comma y such that the partial derivative of f with respect to x equals m, and the partial derivative of f with respect to y equals n. So we will have partial f partial x equals m, which is 3x to the power of half y. We call that equation 1. And partial f partial y equals n, which is 2x to the power of 3 over 2. Let's call that equation 2. We now integrate equation 1 with respect to x, treating y as constant. So if I integrate this, I have f of x comma y equals, integrate this with respect to x, taking y as a constant, we have 3x half plus 1 over y plus a constant of integration, which is a function of y. So we have g of y, and this gives 3x to the power of 3 over 2 y over 3 over 2 plus g of y. And this is the same as 2x to the power of 3 over 2 y plus g of y. Now, we now integrate equation 2 with respect to y, treating x as constant. So if I integrate this with respect to y, I have f of x comma y equals, integrate this with respect to y, treating x as constant, gives us 2x 3 over 2y plus the constant of integration, which is a function of x. So we have h of x. So we have two equations here. F of x comma y equals this, and f of x comma y is also equal to this. So if we compare these two equations, observe that here we cannot find any function of y, no function of y alone here, and also here there is no function of x alone here. So it implies that both h of x and g of y, they are both 0. So it implies that f of x comma y equals to 2x to the power of 3 over 2 y. G of y, or the h of x, equals 0. And so the solution to our differential equation is 2x to the power of 3 over 2y equals an arbitrary constant c. I hope you enjoyed this video. In the next video, we'll look at an example involving the second case. Thank you.